Hello everyone, I am Sonika S, studying MSc in Computer Science at Manasa Gangotri, Mysore. In machine learning, I am going to present the seminar on the topics reinforcement learning, semi-supervised learning, criterion functions for clustering, similarity and dissimilarity measures. So let's see what is reinforcement learning. Reinforcement learning is defined as a machine learning method that is concerned with how software agents should take actions in an environment. Reinforcement learning enables an agent to learn in an interactive environment by trial and error using feedback from its own actions and experiences. There are some important terms used in reinforcement learning. Let's see one by one. The first one is agent. It is an assumed entity which performs actions in an environment to gain some reward. Action. The agent has a set of actions A from which it selects which action to perform. Discount factor. The discount factor is multiplied with the future rewards as discovered by the agent to reduce the effect of the agent's choice of action. Environment. A scenario that an agent has to face. Reward. An immediate return given to an agent when he or she performs specific action or task. State. State refers to the current situation returned by the environment. Policy. It is a strategy which applies by the agent to decide the next action based on the current state. Value. It is expected long-term return with discount as compared to the short-term reward. Value function. It specifies the value of a state, that is the total amount of a reward. It is an agent which should be expected beginning from that state. Model of the environment. This mimics the behavior of the environment. It helps you to make inferences to be made and also determine how the environment will behave. Model-based methods. It is a method for solving reinforcement learning problems which use model-based methods. Q value or action value. Q value is quite similar to value. The only difference between the two is that it takes an additional parameter as a current action. To understand the terms and concept of reinforcement learning, let's take up an example. In the picture, you can see the environment, maybe the garden or a park, consists of the dog, owner of the dog, and a ball. Let's assume the situation where the owner of the dog throws away a ball and the dog will run after the ball and bring back the ball to its owner. So, as a result of an appreciation, the dog will get food as a reward. If the dog does not perform any action, it may get scolding as a punishment. Therefore, this is what reinforcement learning is all about. Let's formalize the example. In the example, the dog is the agent. Action. Just like the dog who decide whether to go after the ball or just look at the ball or jump at the position. Discount factor. Through discount factor, we are making the future rewards less valuable than immediate rewards. This makes the agent look at short-term goals itself. So, lesser the value of discount factor, the more insignificant future rewards will become and vice versa. Environment. In the dog example, the environment consists of the owner and the garden in which the dog is present. It is the environment which gives the agent its rewards as an output based upon the agent's current state and action as inputs. State. A state is an immediate situation in which the agent finds itself in relation to other important things in the surroundings like tools, obstacles, enemies, and prize or rewards. Reward. For example, the dog receives dog food as a reward if the dog, that is agent, brings back the ball, otherwise it receives scolding as a punishment. Policy. Here, policy is the strategy which agent uses to determine the actions which should be taken on the basis of the current state. Basically, the agent maps states to action, that is, it decides the actions which are providing the maximum rewards with regards to states. Talking about the dog example, when the dog comes to know that dog food will be given as a reward if it brings back the ball, keeping this in mind, the dog will create its policy to reap maximum rewards. There are two types of reinforcement learning method. The first method is positive reinforcement learning. It is defined as an event that occurs because of specific behavior. It increases the strength and the frequency of the behavior and impacts positively on the action taken by the agent. This type of reinforcement helps you to maximize performance and sustain change over a more extended period. However, too much reinforcement may lead to over-optimization of state, which can affect the results. The second method is negative reinforcement learning. Negative reinforcement is defined as strengthening of behavior that occurs because of a negative condition which should have stopped or avoided. It helps you to define the minimum stand of performance. However, the drawback of this method is that it provides enough to meet up the minimum behavior. Next is approaches. There are some approaches to implement a reinforcement learning algorithm. The first one is Markov decision process, that is MDP. These are mathematical frameworks that use to formalize the RL problems. If an agent is supposed to decide the best action to select based on his current state. When this step is repeated, this problem is known as MDP. Basically, MDP consists of a set of finite environment states, a set of possible actions in each state, a real valued reward function, and a transition model as well. Next is value-based. In a value-based reinforcement learning method, you should try to maximize a value function. In this method, the agent is expecting a long-term return of the current states under the policy. Policy-based. In a policy-based RL method, you try to come up with such a policy that the action performed in every state helps you to gain maximum reward in the future. Model-based. In this reinforcement learning method, you need to create a virtual model for each environment. The agent learns to perform in that specific environment. Some of the algorithms of reinforcement learning. The first is Q-learning. Q-learning is the most used reinforcement learning algorithm. By the usage of this algorithm, the agent learns the quality of each action based on how much reward the environment returns with. Q-learning uses the table to store the value of each environment state along with the Q value. Second algorithm is SARACA, that is State Action Reward State Action. SARACA resembles Q-learning to a large extent. The only difference between the two is that SARACA learns the Q value based on the action performed by the current policy as compared to Q-learning's way of using greedy policy. Applications of reinforcement learning. Reinforcement learning method is used in many fields such as process control, networking, resource management, robotics, finance, and other. To mention some application, the first one is aircraft control, sensor network, power system, mobile robots, load balancing, option pricing, and signal processing. So these are the some topics of reinforcement learning. Moving on to the concept of semi-supervised learning. So what is semi-supervised learning? Semi-supervised learning is the type of machine learning that uses a combination of a small amount of labeled data and a large amount of unlabeled data to train models. This approach to machine learning is a combination of supervised machine learning, which uses labeled training data, and unsupervised learning, which uses unlabeled training data. Example for semi-supervised learning. As already said, semi-supervised learning is a combination of supervised learning and unsupervised learning. In supervised learning, where a student is under the supervision of a teacher at both home and school. In unsupervised learning, where a student has to figure out a concept himself or herself. And in semi-supervised learning, where a teacher teaches a few concepts in class and gives questions as a homework which are based on similar concepts. So this is what semi-supervised learning is. Semi-supervised learning is further divided into two types. The first one is semi-supervised classification. Semi-supervised classification is similar to supervised approach that require more training data to classify the test data. But in semi-supervised classification, we use less trained data to classify the large amount of test data. By using this semi-supervised classification, we reduce the usage of the training data. Currently, more unlabeled data patterns are available sufficiently in the research community, but the labeled data is not available because to design of the training data is cost effective and time consuming. Second is semi-supervised clustering. Semi-supervised clustering is a special case of clustering. Generally, in clustering, we use unlabeled data patterns for clustering. But in semi-supervised clustering, we use both labeled and unlabeled data with side information as pairwise constraints, which helps to cluster the data patterns. Semi-supervised cluster approach solves the problem of arbitrary shaped cluster. Semi-supervised learning overcomes noisy bridge problem, which is a distance between clusters, by considering the predefined distance matrix with minimal constraints. So, how does semi-supervised learning works? The way that semi-supervised learning manages to train the model with less labeled training data than supervised learning is by using pseudo-labeling. This can combine many neural network models and training methods. So these are the following steps that shows how semi-supervised learning works. The first step is train the model with the small amount of labeled training data just like you did in supervised learning until it gives you good results. Then use it with the unlabeled training data set to predict the outputs, which are pseudo labels since they may not be quite accurate. Link the labels from the labeled training data with the pseudo labels created in the previous step. Link the data inputs in the labeled training data with the inputs in the unlabeled data. Then train the model the same way as you did with the labeled set in the beginning in order to decrease the error and improve the model's accuracy. Next is the assumptions of semi-supervised learning algorithm about the data. In order to make any use of unlabeled data, some relationship to the underlying distribution of data must exist. Semi-supervised learning algorithms make use of at least one of the following assumptions. The first assumption is continuity assumption. The algorithm assumes that the points which are closer to each other are more likely to have the same output label. Second assumption is cluster assumption. The data can be divided into discrete clusters, and points in the same cluster are more likely to share an output label. The third assumption is manifold assumption. The data lie approximately on a manifold of much lower dimension than the input space. This assumption allows the use of distances and densities which are defined on a manifold. Some of the practical applications of semi-supervised learning. The first application is speech analysis. Since labeling of auto files is a very intensive task, semi-supervised learning is a very natural approach to solve this problem. The second application is internet content classification. Labeling each web page is an impractical and unfeasible process and thus uses semi-supervised learning algorithms. Even the Google search algorithm uses a variant of semi-supervised learning to rank the relevance of a web page for a given query. The third application is protein sequence classification. Since DNA strands are typically very large in size, the rise of semi-supervised learning has been imminent in this field. So, these are some of the concepts of semi-supervised learning. The next concept is criterion functions for clustering. Cluster examination isolates information into bunches, that is clusters that are important, valuable or both. In case significant bunches are the objective at that point, the clusters ought to capture the common structure of the information. A great clustering strategy will create tall quality clusters in which the quality of a clustering result too depends on both the similitude degree utilized by the strategy and its usage. The quality of a clustering strategy is additionally measured by its capacity to find a few or all of the covered up designs. So, there are three criterion functions for clustering. The first is internal criterion functions. This class of grouping is an intra-cluster view. Internal basis work upgrades a capacity and measures the nature of bunching capacity different groups which are unique in relation to each other. The second one is hybrid criterion functions. This work is utilized because it has the capacity to at the same time optimize numerous person model capacities, not at all like as inside basis work and outside basis work. The third is external criterion function. This lesson of clustering measure is an inter-class view. External basis work optimizes a work and measures the quality of clustering capacity of different clusters which are diverse from each other. The next concept is similarity and dissimilarity measures. So what is similarity measure? It is a numerical measure of how alike two data objects are. It is higher when objects are more alike. It often falls in the range 0, 1. Similarity might be used to identify the duplicate data that may have differences due to typos, equivalent instances from different data sets, example names and or addresses that are the same but have misspellings, and for groups of data that are very close, that are clusters. Next is dissimilarity measure. It is a numerical measure of how different two data objects are. It is lower when objects are more alike. Minimum dissimilarity is often 0, while the upper limit varies depending on how much variation can be. Dissimilarity might be used to identify outliers, interesting exception, that is credit card fraud, and for boundaries to clusters. So some of the similarity and dissimilarity measures are: the first one is Euclidean distance. Euclidean distance is the most common use of distance measure. In most cases, when people say about distance, they will refer to Euclidean distance. Euclidean distance is also known as simply distance. When data is dense or continuous, this is the best proximity measure. The Euclidean distance between 2 points is the length of the path connecting them. The Pythagorean theorem gives this distance between 2 points. Next is Manhattan distance. Manhattan distance is a metric in which the distance between 2 points is calculated as the sum of the absolute differences of their Cartesian coordinates. In a simple way of saying, it is the total sum of the difference between the x coordinates and y coordinates. Suppose we have 2 points A and B. If we want to calculate the Manhattan distance between them, just we have to sum up the absolute x-axis and y-axis variation. This means we have to find how these 2 points A and B are varying in x-axis and y-axis. In more mathematical way of saying, Manhattan distance between 2 points measured along axis at right angles. In a plane with P1 at x1, y1 and P2 at x2, y2. Manhattan distance is equal to mod of x1 minus x2 plus mod of y1 minus y2. This Manhattan distance metric is also known as Manhattan length, rectilinear distance, L1 distance or L1 norm, city block distance and taxicab metric. Next is Minkowski distance. The Minkowski distance is a generalized metric form of Euclidean distance and Manhattan distance. In the above equation, d to the power of mkd is the Minkowski distance between the data record I and j, k is the index of a variable, n is the total number of variables, y and lambda the order of the Minkowski metric. Although it is defined for any lambda greater than 0, it is rarely used for values other than 1, 2 and infinity. The way distance are measured by the Minkowski metric of different orders between two objects with three variables. In the image is displayed in a coordinate system with x, y, z axis. Synonyms of Minkowski. Different names for the Minkowski distance or Minkowski metric arise from the order. If the lambda value is 1, it is the Manhattan distance. Synonyms are L1 norm, taxicab or city block distance. For two vectors of ranked ordinal variables, the Manhattan distance is sometimes called foot ruler distance. If the value of lambda is 2, it is the Euclidean distance. Synonyms are L2 norm or ruler distance. For two vectors of ranked ordinal variables, the Euclidean distance is sometimes called Spearman distance. If the value of lambda is infinity, it is called Chebyshev distance. Synonyms are L-max norm or chessboard distance. Next is cosine similarity. The cosine similarity metric finds the normalized dot product of the two attributes. By determining the cosine similarity, we would effectively try to find the cosine of the angle between the two objects. The cosine of 0 degree is 1 and it is less than 1 for any other degree. It is thus a judgment of the orientation and not magnitude. Two vectors with the same orientation have a cosine similarity of 1. Two vectors at 90 degree have a similarity of 0, whereas two vectors diametrically opposed having a similarity of -1 independent of their magnitude. Cosine similarity is particularly used in positive space, where the outcome is neatly bounded in 0, 1. One of the reasons for the popularity of cosine similarity is that it is very efficient to evaluate, especially for space vectors. Next is Jacquard similarity. For Jacquard similarity, we have to consider some of the set operations like cardinality, intersection and union. In this example, we can observe set A consists of 4 elements and set B consists of 5 elements. The Jaccard similarity measures the similarity between finite sample sets and is defined as the cardinality of the intersection of sets divided by the cardinality of the union of the sample sets. Suppose you want to find Jaccard similarity between two sets A and B. It is the relation of the cardinality of A intersection B and A union B. In the above example, the cardinality of A intersection B is equal to 2 and the cardinality of A union B is equal to 7. So, the Jaccard similarity is equal to 0.286. Thank you.